We're now ready to find some rules for finding the derivatives of various functions, because we're going to need derivatives and we want to be able to find them quickly. Using the definition of derivative, the limit as h approaches 0, that difference quotient can be very time consuming, can be very messy algebraically. So first let's look for some rules that will enable us to take derivatives of polynomial functions. The simplest of polynomial functions would be a polynomial of degree 0. So if we have f of x equaling a constant, we can see here that any secant line and any tangent line would have a slope of 0. So the derivative of a constant is going to be 0. Now let's look at x to the first power. And so we have our identity function here. If we look at the graph, we see that any secant line and any tangent line, the slope there would equal 1 at any given x value. Therefore, the derivative of x equals 1. Now, what about higher powered x's? We could look for the derivative of x to the nth power. And for that, we're going to have the power rule. And following this video is a link to the proof of the power rule. And it's important to watch this to see how this is developed, and it's always when we need rules for derivatives, find a derivative of something we don't know, we're going to go back to that definition, the limit as h approaches 0 of the slopes of those secant lines. The power rule says if n is a positive integer, then the derivative of x to the n equals n x to the n minus 1. So looking at this, the way that I think of the power rule is I always say that it basically is multiply the power out in front, so a factor of n, and then decrease the power by 1. This is essentially what we find as we write this out using the definition of derivative. So power rule, power out in front, and then x to the one smaller power, so to the n minus 1 power. Now, it turns out if I needed the derivative of 1 over x, or 1 over x squared, we know that we can express these in terms of a negative exponent. And so this one I could write as x to the negative 1, this one as x to the negative 2, and it turns out the power rule applies whether the exponent is positive or negative. So if I wanted to find the derivative of x to the negative 2, I could apply this power rule, which says multiply the power out in front and then decrease the power by 1. So this would be negative 2 over x to the third, because this of course is x to the negative 3, and then I can express that without a negative exponent like this. Now it also turns out that we know that the square root of x could be expressed, this radical could be expressed as a rational exponent, and so we could express this as x to the 1/2. And it turns out that the power rule applies when n is any real number. So it doesn't have to be an integer, it doesn't have to be positive, it could be positive or negative, and it could be a rational number, any real number in fact. And so as we apply the power rule here, basically we multiply the power out in front and then we decrease the power by 1. And of course our power was 1/2, and if we decrease that by 1, we get 1/2 minus 2/2, which is negative 1/2. So the power rule applies when we have x to the n, where n is any real number. Now we're going to look at the constant multiple rule, and again the proofs of this follow this video, but this should be fairly easy to see because we know we can write derivatives in terms of limits, and we know from our limit laws that if you multiply a limit, you have the limit of a constant multiplied by a function, that you can do the limit first and then multiply the constant later. And so if u is a differentiable function of x and c is a constant, then the derivative of a constant times this function is the derivative of the function and then multiplied by the constant. So that's just essentially using that limit law. So in fact, if I wanted to compute this derivative, I could multiply the constant later, and I could find the derivative of x squared, and we know that's a power rule. Power out in front, decrease the power by 1, and then we will multiply it by the constant. So we should get the derivative of 3x squared is 6x. Looking at this graphically, you can see that if we just had the function y equals x squared and we looked at the slope would be 2x. For a given x, for example, if x equals 1, we could substitute a 1 in here and we see that the slope is 2. Now, if we take a function that is 3 times x squared, then the slope ends up being 3 times 2x, and you can see if we looked at it at 1, this slope is 6, which is 3 times the slope of our function x squared. So we can do the constant later so that we can go ahead and use our rules. We can use our power rule to find the derivative of x squared and then multiply by the constant. Now, if we needed to take the derivative of a sum of two functions, again, because we can go back to the limit definition of the derivative, then limit laws would apply, and we know that if we want the limit of a sum, we can take the sum of the limits. Therefore, the sum rule, if we have f and g that are differentiable functions at x, then the derivative of the sum f plus g equals the derivative of f plus the derivative of g. This is also going to be true if this was not a sum but a difference. And so with the difference, same thing, because we know that if we had the limit of a difference, it would be the difference of the two limits. So we could, if we had the derivative of f of x minus g of x, that would equal the derivative of f of x and then the derivative of g of x, and taking the difference. These rules are going to be very important because they will enable us to find derivatives of polynomials very quickly, because essentially polynomials are going to be comprised of multiples of powers of x and various terms added or subtracted. So by combining all of these rules, we'll be able to differentiate all polynomials very quickly. Make sure you look at the proofs to see how these rules are derived, and also make sure you then look at the examples so you can see how we would apply all of these rules to polynomials.